In this video, we're going to talk about products and powers of the exponential form of complex numbers, as well as roots of complex numbers. This is our overview slide, which we'll spend about 5 minutes going over before we go over each of these topics in more detail and with more examples. First, we will talk about the products of exponential form. So if we have two complex numbers written in exponential form, so that z1 is equal to r1 e to the I theta 1, and z2 is equal to r2 e to the I theta 2, then z1 times z2, we multiply our two radius, r1 and r2 together, and then we multiply our e to the I theta 1 times e to the I theta 2, was essentially e to the I theta 1 plus theta 2. So if we think of multiplying z1 by z2, then the radius of z1 is scaled by r2, and the angle of z1 then gets an additional rotation by theta 2. Similarly, z1 divided by z2 is equal to r1 e to the I theta 1, r2 e to the I theta 2, so you have the ratio of r1, r2. You have e to the I theta 1 minus theta 2. And we want to note that z to the negative 1 is 1 over r e to the minus I theta. The next topic we will go over are the powers. So z to the n then is equal to r to the n e to the I n theta. And we have de Moivre's formula, which is e to the I theta. So if we take this complex number, raise it to the n, that will be equal to cosine theta plus I sine theta raised to the n, which is equal to cosine n theta plus I sine n theta. And we have these two examples. This first one is about raising a complex number, square root of 3 plus I to the 7th. The first thing we do is convert our complex number, 3 plus I, to exponential form, which is 2e to the I pi over 6. We'll go over this in more detail later in the video, but we raise that to the 7th, which means we get 2 to the 7th and e to the I 7 pi over 6. And then there's some further reducing and then converting back to our Cartesian coordinate kind of form. The other example we'll go over is de Moivre's formula, and we'll look at cosine theta plus I sine theta all squared. Using the formula, that will be equal to cosine 2 theta plus I sine 2 theta. The next topic we have is this property about the arguments of products and quotients. First, just to kind of quickly review what an argument is, it's when we converted a complex number using polar coordinates, and we solved for x, we solved for y, or then we can solve for theta here, for cosine theta, sine theta. The thing about the theta is that once you have solved for theta, you can add any integer multiple of 2 pi, and you have another angle theta that will be equivalent to your original theta. So the idea is arg z is your angle theta. It's all the sets of angles that is equivalent to theta. That is, it's going to be what we call capital arg z, which is theta, the theta that it's between negative pi and pi, plus all multiples of 2 pi. So that's little arg z is all the possible thetas. Your capital arg z is the particular theta that satisfies the condition it's between negative pi and pi. So when we take the product of two complex numbers, z1 and z2, then the argument with lowercase of z1, z2 is equal to arg z1 plus arg z2. Similarly, for arg z1 divided by z2, that will be arg z minus arg z2. And if the values of 2 of the 3 multiple arguments are specified, then there is a value of the third such that the equation holds. And we'll do examples of this as well. Last, we'll look at roots of a complex number. So if we have a complex number z and we want the nth root of it, so we have the nth root of r1 e to the I theta 1, that will be the nth root of r1, and then the nth root of e to the I theta 1, which is e to the I theta 1 plus 2 pi k over n, because our solutions, it's not just theta 1 over n, but theta 1 over n plus any integer multiple of 2 pi k. So for example, if we want the roots of negative 8I to the 1/3, that will give us then the third root of r1, which is 2 over here, or a third root of 8, which is 2. And then we're going to have I, which we write I as negative I pi over 2. And again here, our negative pi over 2 is using our capital argz, the value of theta between negative pi and pi. So I can be expressed as negative pi over 2 when we take the third root. That will give us negative I pi over 6. And then we need to add 2 pi over k divided by 3. So this is our final answer. We'll do some other problems where these two, what are these? These are double angle formulas? Yeah, double angle formulas will become convenient. That is our quick overview. So now let's start back up here with products of exponential form. Take a closer look at that and do some more examples. First, we'll look at products of the exponential form. So if we have our first complex number, e to the I theta 1, multiplied by our second complex number, e to the I theta 2, we can just use our properties of exponents and say that is equal to e to the I theta 1 plus theta 2. We can also look at this from the point of view of Euler's equation. So e to the I theta 1 can be converted to cosine theta 1 plus I sine theta 1. Similarly, e to the I theta 2 can be converted to cosine theta 2 plus I sine theta 2. We can do the multiplication, group our imaginary parts together, and what we get is e to the I theta 1 plus theta 2. So exactly what we would get just using simply the exponential law formulas. Then, just to be complete, let's add the radius r1. So if z1 is equal to r1 e to the I theta 1, and z2 is equal to r2 e to the I theta 2, then z1 times z2 is equal to r1 r2 e to the I theta 1 e to the I theta 2, which is equal to r1 r2 e to the I theta 1 plus theta 2. We also have the division. Z1 over Z2 is r1 e to the I theta 1 over r2 e to the I theta 2 using properties of exponents, and also just our constant multipliers. We pull out r1 over r2 e to the I, then our exponent laws will give us theta 1 minus theta 2. And finally, let's just note that z to the minus 1 is 1 over z, which is 1 over r e to the minus I theta. Now that we've reviewed the products of the exponential form, we can look at the powers of a complex number. So z to the n will be equal to r to the n e to the I n theta. Our first example will be to convert to rectangular form square root of 3 plus I, all raised to the 7th. In other words, the 7th power of this complex number square root of 3 plus I. The first thing we want to do is convert the square root of 3 plus I into exponential form. Here I have graphed, so on the real axis I have square root of 3, and on the imaginary axis my I is multiplied by 1. So here I have square root of 3, on the y I have 1. So the radius is square root of 3 squared plus 1 squared, which is equal to 2, and then my tangent of theta is going to be equal to 1 over square root of 3, so theta is equal to pi over 6. Which means my square root of 3 plus I to the 7th is equal to 2 e to the I pi over 6 raised to the 7th. Separating out the constant, I have 2 to the 7th, e to the I 7 pi over 6. I'm going to separate out a factor of 2 from this 2 to the 7th so I can associate this with e to the pi over 6 so that later I can group this together as my original 2e to the pi over 6. So I'm going to have 2 to the 6th e to the I pi, and then my 2 times e to the I pi over 6. This e to the I pi is equal to negative 1. 2 to the 6 is 64. So I have that this square root of 3 plus I to the 7th is negative 64 square root of 3 plus I to the 7th. When we talk about powers of a complex number, that will lead us to de Moivre's formula, which comes from e to the I theta n is equal to e to the I n theta. Converting this formula to trigonometric form, that means e to the I theta is equal to cosine theta plus I sine theta. So when we raise that to the n, that's equal to, using Euler's now on this side of the formula, will equal to cosine n theta plus I sine n theta. Our first example is to use de Moivre's formula to evaluate cosine theta plus I sine theta squared. And this is pretty straightforward. So we have cosine theta plus I sine theta squared, which is equal to e to the I theta, just converting this using Euler's, squared, which is e to the I 2 theta. So again, using Euler's now on this will give us cosine 2 theta plus I sine 2 theta. Furthermore, I can use this result here to derive two trigonometric double angle formulas. So squaring cosine theta plus I sine theta will give us cosine squared minus sine squared plus 2I cosine theta sine theta. Again, that's just this part here, just comes from cosine plus I sine theta squared. By de Moivre's formula, that's going to equal to cosine 2 theta plus sine 2 theta. Now equating the real part of the left-hand side of the equation with the real part of the right-hand side of the equation, so the real part here is cosine squared theta minus sine squared theta, that will equal to cosine 2 theta. Equating the imaginary part of the left-hand side of the equation with the imaginary part of the right-hand side equation, we get 2 cosine theta sine theta is equal to sine 2 theta. So these are our two trigonometric double angle formulas that we derived from de Moivre's formula. Our next topic is about arguments of products and quotients of complex numbers. If you remember, the argument that relates to the angle theta. So lowercase arg z are all the thetas that are equivalent to this theta here, and this theta, basically you can add any multiple of 2 pi to theta, and you still have an equivalent angle. The capital arg z, capital A R G Z, that's the particular angle where theta is between negative pi and pi. So over here we talked about how when we had a product of two complex numbers, we would be rotating our first complex number by an additional theta 2. So you can see the similarity in the equation here. The argument or the angle when you multiply two complex numbers will give you the argument, or basically you add the angle of z1 plus the angle of z2. The only problem is sometimes your angles might differ by 2 pi. So this is saying, what this rule is saying is that if the value of 2 of the 3 of these arguments are known, then there's a value of the third such that the equation holds. And we'll do an example of that. And we also have this other similar formula, corresponding formula, arg of z1 divided by z2 is equal to arg z minus arg z2. As I had mentioned, this stuff with the arguments of products and quotients is probably best seen with an example. So let's let z1 equal negative 1 and z2 equal to I. I have drawn here negative 1 and I, and I also drew negative 1. I don't know why, just because. So negative 1, so the argument of negative 1, so for starting here, we need to go around pi radians to get to negative 1. And then to get to pi, we need to go over pi 2 radians. So arg of z1 is equal to pi, and arg of z2 is equal to pi over 2. And you'll notice I put arg with the capital A because in this case, the angles we are talking about are between negative pi and less than or equal to pi. So these two are our principal arguments. Now, if we multiply z1 by z2, we're going to get negative I, which is what I have graphed here. The argument of negative I, so we come around from here to here, that's 3 pi over 2 radians. And actually at this point, I need to be careful because 3 pi over 2 is not our principal argument. 3 pi over 2 is greater than pi, so I should really make these lowercase. If I really want to find the principal argument, and I do, for this negative I need the angle between negative theta and theta, but that's just this angle over here. I can go in the opposite direction, in the clockwise direction, and get negative pi over 2 as my angle. It's easy to see this negative pi over 2 gets us to negative I, and you can see that that would be a principal argument because it's between negative pi and pi. But you can also think of this as our original 3 pi over 2, our little arg z, and then we can add some integer multiple of 2 pi. In this case, we decided to subtract 2 pi. We could have added 2 pi, but then we would have gotten even more positive, and we still wouldn't be anywhere near our principal arg. So let's try subtracting 2 pi, which is just, so the positive direction is this way. So the negative direction is clockwise. So if we're here at 3 pi over 2, and then we go clockwise, pi over 2, you can see we end up in the same, at the same point. So 3 pi over 2 minus 2 pi will give us our negative pi over 2. What you have then is arg of z1 z times z2 is equal to 3 pi over 2, which is the principal argument of z1 plus the principal argument of z2. And all that this formula guarantees, it doesn't have to be the principal argument here. It just so happens here it's the principal argument. But the other thing that this formula is supposed to tell us is it's not that any argument of z1, z2. So for example, if we took argument of z1, z2 and we used negative pi over 2, and then you can see that that's not equal to arg z1 here and the principal argument z2. But there is, if we had these two values, z1 and z2, then we can find a third value in the space of the lowercase args that satisfy the equation. In particular, if we have arg z1, z2, which is 3 pi over 2, it's these two values here that will satisfy the equation. So another example, find the principal argument of z equals negative 2 divided by 1 plus square root of 3i. And we want to use these properties here of arguments of products and quotients to find the principal argument of this complex number. I started by graphing my 1 plus square root of 3i. I know what negative 2 looks like, right? It's over here. So I've graphed my 1 plus 3i, and what I'm going to say is arg z, this is my z, is going to be equal to arg of negative 2 minus my arg of 1 plus 3i. And I'm using this formula up here, which is the quotient formula for my arguments. The argument of negative 2 over here, that looks like pi to me, which is good. It's also a principal argument. Arg of 1 plus 3i. So what I need to do is find tangent of theta is equal to, in this case, we have our x-coordinate is, our y-coordinate is square root of 3. Our x-coordinate is equal to 1. So tangent of theta is equal to square root of 3, which implies theta is equal to pi over 3, which means the argument of 1 plus 3i is equal to pi over 3. And by our formula here, that means arg z is equal to pi minus pi over 3, which is 2 pi divided by 3. Now, since 2 pi divided by 3 is between negative pi and pi, that is also our principal argument. Our last topic is roots of a complex number. We will consider the nth root of the complex number r1 e to the I theta 1. So we can take out the constants. So we have the nth root of r1. Then using the rules of exponent, we have e to the I theta 1 divided by n, which is over here. And also, because we're solving, for the nth root, we also have to take into account that we have not only theta 1, but any integer multiple of 2 pi plus theta 1. So that's what this equation is here. So we have the nth root of r1, the exponent e to the I theta 1 plus 2 pi k over n, where k is any positive or negative integer 0, 1, 2, 3, etc. This point over here, where we need to take into account theta 1 plus 2 pi k, comes from this fact that if we have two complex numbers, z1, z2, where z1 is equal to r1 e to the I theta 1 and z2 is equal to r2 e to the I theta 2, then z1 is equal to z2 if r1 is equal to r2 and theta 1 is equal to theta 2 plus 2 pi n, where n is any integer, including 0. So the thing that often gets forgotten is it's not simply theta 1 equals theta 2, but theta 1 equals theta 2 plus 2 pi n. So that's why this part here is necessary. And then that is exactly how we get this formula here, which is copied down here, that the nth root of r1 e to the I theta 1 is nth root of r1 and e to the I theta 1 over n plus our 2 pi k over n as well. And our three other points. So we shall let z naught 1 to the n denote the set of nth roots of z naught, and that n square root of r naught, so this particular notation with the square root sign is reserved for the one positive square root. And last, when theta naught is the principal argument of z naught, that is, theta naught is between negative pi and pi, then that z naught, the corresponding z naught, is called the principal root. Our first example is to find all the roots of negative 8i raised to the 1/3. That is, we want to find the three cube roots of negative 8i. The first thing we want to do is express our negative 8i in exponential form. So let's just take a look at negative I, and negative I corresponds to the angle where theta is equal to negative pi over 2. You could have expressed this as 3 pi over 2 if you went this direction, the normal positive direction. That would be theta equals negative 3 pi over 2. But because I want to use the principal argument, I'm going to use negative pi over 2. So what we have is 8e to the minus pi over 2i. And I want to remember I can add any multiple of 2 pi, and I have still the same angle, still the same number. Now if I want to take the cube root, I'm going to take the cube root of my constant, and I'm going to divide my exponent by 3. So e to the I minus pi over 6 plus 2 pi k divided by 3. Our cube root of 8 gives us 2, and then we have I e to the I minus pi over 6 plus 2 pi k over 3. Which means my three roots are, if I let k equal to 0, 2e to the I pi over 6. If I let k equal to 1, that's 2e to the I negative pi over 6 plus 2 pi over 3, which is 2e to the I pi. And when k is equal to 2, I'm going to get 2e to the I pi over 7. When k is equal to 3, this becomes 2 pi, and we've looped back around to 2e to the I pi over 6. I can draw this pictorially, so my first root is 2 times e to the minus I pi over 6, so that's this angle here, out a radius of 2. My second root is 2e to the I pi, so that's over here. And my third root is 2e to the I pi, 7 pi over 3, which is here. What you can see what we're doing is we're starting for one root, and then we're adding our 2 pi over 3 to get to our next root, and then adding another 2 pi over 3 to get our next root. And then when we add another 2 pi over 3, we've come back to our first root over here. Our principal root then is the theta that lies between negative pi and pi, so that will be negative pi over 6, which means our principal root then is equal to 2 cosine negative pi over 6 minus, oh, I guess this should be plus, I sine minus pi over 6. Oh, I see. The minus was there because sine's an odd function, so you can get rid of this negative here and make this negative instead. So I made that adjustment here. I condensed my work over here. Here's my z. Here's when I took the cube root of z, and I named the three roots, when k equals 0, k equals 1, k equals 2. And I identified my principal root as 2e to the minus I pi over 6. And I cleared out this room because I wanted to put this back into kind of a Cartesian coordinate look or form. To do that, I'm going to use these two double angle formulas that I did list on your overview slide. I am going to start with cosine squared pi over 6, then using this double angle formula is equal to 1/2, so I just pulled out the 1/2, 1 plus cosine, and now I just double this angle here. So cosine pi over 3. Doing the calculation, what I get is 3 pi over 4, 3/4. So then cosine is going to be, this is cosine squared, so cosine of pi over 6 is going to be square root of 3 over 2. Similarly, sine squared of pi over 6 will be equal to 1/4, which means sine of pi over 6 equals 1/2, which means now I'm going to come over here where I have the formula for my principal root, which I'm going to underline in green. So my 2, get my pointer, 2e minus I pi over 6 over here is equal to 2 times cosine of pi over 6, which is square root of 3 over 2. And then I have minus I sine of pi over 6. So sine of pi over 6 is 1/2, so I have minus 1/2 I, which is equal to square root of 3 minus I. So this will be my final answer here. Our last example is to find all the nth roots of 1, which is kind of strange because, how many roots could 1 possibly have? That makes the nth root of 1 equals to e to the I 2 pi k to the n, and this is our answer. So for example, when n is equal to 2, in other words, the square root of 1, we have e to the I, when n is equal to 2, the 2's cancel out and we get pi k. So when k is equal to 0, we get e to the 0, which is 1. When k is equal to 1, we get e to the I pi, which is negative 1. And when k is equal to 2, we get e to the I 2 pi, which is back to 1. So we have these two roots here. We have 1 and negative 1, which is what we would expect. When n is equal to 3, we're looking for the cube roots of 1, and we have e to the I 2 pi k over 3. So when k is equal to 0, again we have e to the I 0, e to the 0, which is 1. When k is equal to 1, we have e to the I 2 pi over 3. When k is equal to 2, we have e to the I 4 pi over 3. And when k is equal to 3, we loop back around. So we have these 3 roots. What this looks like is we start at 1, and then we go around 2 pi over 3 to get our next root. And here we have e to the 2 pi over 3. We go over another 2 pi over 3. We get our next root, e to the I 4 pi over 3. And then finally, when we go another 2 pi over 3, we come back to our original root of 1. So I kind of reduced and moved my n equals 2, n equals 3, so we could look at n equals 4. So plugging in n equals 4 into this formula for the fourth root of 1, we're going to have e to the I 2 pi, e to the I pi k over 2, because the 4 simplifies with the 2. So when k equals 0, again we get 1. When k equals 1, we're going to get e to the I pi over 2, which is I. When k equals 2, we get e to the I pi, which is negative 1. And when k is equal to 3, we get e to the I 3 pi over 2, which is equal to I. And when k equals 4, we come back and loop around to our original root. So k equals 0, k equals 1, we get I. K equals 2, we get negative 1. And k equals 3, we get negative I. And then we loop back around. To summarize what we have covered in this video, we talked about products and powers of the exponential form of complex numbers, as well as roots of the complex numbers. So first we looked at products of the exponential form of complex numbers. So if we have a complex number z1, z2, we said z1 times z2 is equal to the radius parts, r1 times r2, times the e to the I theta 1 and e to the I theta 2, and by rules of exponents, we can combine these theta 1 and theta 2, so we get r1, r2, e to the I theta 1 plus theta 2. We have a similar result for z1 divided by z2, and we also have the note that z to the negative 1 is equal to 1 over z, which is equal to 1 over r, e to the minus I theta. Next, we talked about powers of a complex number, which is simply r to the n, e to the I n theta. From there, we had De Moivre's formula, which is e to the I theta raised to the n. Using our powers here, that would just be equal to e to the I n theta. Now, De Moivre says if on this side we plug this into Euler's formula, our e to the I theta becomes cosine theta plus I sine theta. We raise that to the n. And then on the right-hand side of the equation, we plug in e to the I n theta into Euler's, and we get cosine n theta plus I sine n theta. And we did a couple of examples, both with the powers and De Moivre's formula. We additionally had another example using De Moivre's formula to produce the half-angle, trigonometric half-angle formulas. Next, we talked about arguments of complex numbers and how they relate to the products and quotient of complex numbers. So in particular, arg z1 times z2 is equal to arg z1 plus arg z2 for two complex numbers, and arg z1 divided by z2 is equal to arg z1 minus arg z2. And the only thing you want to remember is there are many arguments for a single complex number. So you can't just plug in any of the arguments for z1, z2, and any argument for z1 and any argument for z2. What this formula says is that there is a value for the third such that the equation holds. So it may not be the principal argument across the line, across these three, but if you choose two values, then you will be able to find another argument that might differ by 2 pi from the principal value, 2 pi n from the principal value, that will satisfy this equation. And we did some examples. Finally, we looked at roots of complex numbers, and we used this formula here. The nth root of r1 e to the I theta 1 is equal to the nth root of r1 times e to the I theta 1 over n plus 2 pi k over n. And the thing we want to remember here is that for any complex number, if we add 2 pi, some integer multiple of 2 pi to our argument theta 1, we will still get an equivalent complex number. We did some examples, such as this third root, or the cube root, of negative 8 pi. And we also converted back into kind of Cartesian coordinate form using these double angle formulas. So that is it for this video. Thank you for watching.